Hello and welcome to Void Electronics. In today's video I want to talk about the oscilloscope. More specifically, I want to talk about what an oscilloscope is, how to use it, what is it made of, and finally some traps for young players. So let's get started. First of all, let's talk about what the oscilloscope is. The oscilloscope is a piece of test equipment that allows you to visualize signals with respect to time. This is especially important because in electronics we have all sorts of graphs that are not necessarily with respect to time. We have graphs that represent current versus temperature, voltage versus temperature, amplitude versus frequency, like in the case of a spectrum analyzer, IV curves, and even one voltage versus another, like in the case of Lissajous patterns. Before the oscilloscope took the form that we know today, during the 19th century there were all sorts of electromechanical contraptions that would allow you to visualize waveforms. One example of such early device is the Hospitalier ondograph invented by André Blondel. This device allowed you to plot waveforms on paper with a bandwidth of less than 20 kHz. These electromechanical devices were revolutionized in 1897 when a German physicist called Carl Ferdinand Braun invented the CRT. After that, a British company called A.C. Cossor started producing CRT oscilloscopes as early as 1932, and those are probably the earliest devices that resemble an oscilloscope as it is today. So for today's demo I would like to use the CRT oscilloscope because in my opinion it is a lot easier to understand than a digital oscilloscope. After demonstrating some basic principles on this oscilloscope, we will move on to the digital oscilloscope to see what advantages it has with respect to the analog oscilloscope. So let's start with the basics by reinventing one of those electromechanical contraptions. If I move my hand up and down like this in a sinusoidal motion and then I also drag the paper with constant speed from left to right, I should get a plot of my hand's movement with respect to time. So let's see if that works. So as you can see, we managed to make our own primitive plotting device, and now let's see how this relates to the oscilloscope. Before this video gets boring with even more theory, let's look at an actual CRT. So the CRT was invented by Carl Ferdinand Braun in 1897 based on previous experimental tubes developed by Heinrich Geissler or Sir William Crookes. This is what an oscilloscope CRT looks like. As you can see, it's pretty small, it has a phosphor screen, and in the back it has what we call an electron gun. This device, as the name suggests, produces a stream of electrons that get accelerated from this end of the tube all the way to the screen. To do this, the electron gun has a cathode which is heated until it's red hot by a heater which is similar to the filament we had in incandescent light bulbs, if anybody remembers those. In front of the cathode we have all sorts of electrodes that basically focus the electrons into a tight beam. These electrodes are the electrostatic equivalent of optical lenses basically. After these electrodes, somewhere hidden behind this shield are the deflection plates, which allows us to deflect the beam either horizontally or vertically. And finally, this area of the tube is called the anode, and its purpose is to accelerate the electrons from the cathode all the way to the phosphor screen. The anode has a high voltage connection that you can see here, and it's usually powered by a high voltage low current source. So for really small tubes we are talking about voltages of maybe a few hundreds of volts, and for color TV CRTs the voltage can get as high as 25 kilovolts. Normally I would just build a circuit and power up the CRT that we saw on the bench. However, CRTs are pretty inconvenient to run in a hobby environment. For this reason, I will take advantage of this fully working oscilloscope that we have in front of us. So now let's see the basics of what a CRT can do. So by applying all the right voltages, what we get is a dot that looks something like this. This is not very useful because the dot is very large, as you can see. However, by applying the right focus voltage on the focus electrode, we can focus this into a really tight dot. One that looks something like this. Now a dot like this is not really useful unless we have some means to move it across the screen. And that's exactly what the oscilloscope does. So by varying the voltage on the deflection plates, the oscilloscope can move this dot left or right and also up and down. So this is how we control the horizontal axis. And this is how we can control the vertical axis. And now let's see how this relates to actually plotting a signal with respect to time. So here we have this power supply which is connected to channel 2 of this oscilloscope. This channel also controls the vertical axis in XY mode, which is what we are doing for today's demonstration. So as you can see, by changing the voltage setting on this power supply, we can make the dot move up or down. So this vertical control solves half of the problem of plotting the signal with respect to time. Let's see how we can now solve the other half. Well, that's pretty easy. First of all, for this demonstration, we can take advantage of the storage functionality of this scope in order to have an image that has some persistence on the screen. Now we can once again vary the voltage. And now all we need to do is to move the dot at constant speed from left to right, and this way we can get a plot of the signal with respect to time. So now, just for fun, let's repeat this demonstration with an actual sine wave at the input. So here we have a 1 Hz sine wave, we will enable the storage once again, and now by moving the beam at constant speed from left to right, we should get something that resembles a sine wave. This is not really a sine wave because I cannot move the beam exactly at constant speed, but you get the point, and you probably get the similarity between this and the plot that we did on paper. Now obviously by slightly changing the settings on the oscilloscope, that left to right sweep at constant speed is produced automatically. So this way we are one step closer to that ideal sine wave that we all know. And now to take things a step further, I can demonstrate that the oscilloscope can go much faster than this. Actually, in all the demonstrations that you've seen so far, the oscilloscope was about as slow as it can get. So let's change the settings here just a bit. For example, let's observe a 1 MHz signal. The first step is to set the signal generator to 1 MHz. Then we'll set the oscilloscope to auto mode. And now we can make the time base a lot faster so that we can actually see the 1 MHz signal. Let's adjust the trigger just a bit. And now as you can see, we get a really nice sine wave on the screen. Notice how the sweep is so fast that we no longer see a sweep from left to right, but keep in mind the oscilloscope is doing exactly the same thing, but it just happens a lot faster. So it's still doing something like this. And now let's talk about the three main subsystems that all oscilloscopes have. Let's start with the vertical system. If you remember from the previous demos, the vertical system is directly driven by the input. In order to adjust the vertical size of the input on the screen, and also in order for the oscilloscope to be able to visualize both very high amplitude signals and very low amplitude signals, we have this sensitivity setting here in volts per division that allows us to accommodate for all that. And also here we have a vertical position knob that allows us to move the signal up and down on the screen. Also, the vertical system usually has at least three options for input coupling. We have ground, in which the input is basically decoupled from the oscilloscope, DC, in which the input is directly coupled to the oscilloscope, and also AC, in which the input is coupled through a capacitor so that you can remove the DC offset of the signal. To apply all these, let's measure the amplitude of this signal. Let's look at the settings on the signal generator so that we know what to expect. So here we have a 1 MHz signal with a 2 volts peak-to-peak amplitude and a 1 volt offset. Now back to the oscilloscope to see what that looks like. As you can see, the signal is sort of shifted upwards, and that's due to the 1 volt offset that we've set on the signal generator. So by adjusting the coupling here, we can get rid of that 1 volt offset because we don't care about it when we measure the amplitude. So let's set the coupling to AC. As you can see, the signal shifted down because now the DC component was removed. And now to measure the amplitude, we need to look at the vertical sensitivity. So here we have 0.5 volts per division. So the first step is to align the signal with one of the horizontal lines that we have on the screen. For this we can enable the scale illumination so that we can see the lines just a little bit better. And now let's align the bottom of this sine wave to one of the horizontal lines that we have here. For example, we can do something like this. And now to measure the amplitude, we have to look at the vertical span of our signal on the screen. So our signal spans 1, 2, 3, 4 divisions. 4 divisions multiplied by 0.5 volts per division gives us an amplitude of 2 volts peak to peak. And now, in case we're interested in measuring the DC offset as well, we can look at the bottom of the signal where it is right now, and then we can change the coupling to DC coupling to see how many divisions the signal goes up. Our signal moved by exactly 2 divisions, multiplied by 0.5 volts per division, which means that the DC offset of this signal is 1 volt. As you can see, the results of our measurements perfectly match the settings that we have on the signal generator. And this concludes the presentation of the vertical system. Now let's talk about the horizontal system. The horizontal system consists of an oscillator that produces a left to right sweep at constant speed. This oscillator is called a time base. Basically, for fast signals we want a fast time base, and for slow signals we want a slow time base. And the setting for that is the setting that we can see right here, which is in time per division, or seconds per division, or in the case of an oscilloscope, it's usually set in sub-multiples of seconds per division. As you can see, by changing this setting we can choose the number of periods that we can see on the screen in case we're talking about a periodic signal. And now, similarly to what we did with the vertical system, let's do a measurement to demonstrate the horizontal system. This is a bit hard to see, but the setting right here is 0.5 microseconds per division. And now I will use this horizontal position knob to make one peak of this sine wave align with one of the vertical lines that we see on the screen. For example, this peak is now aligned to this line right here. And now I just have to count the number of divisions until the next peak. So we have 1, 2 divisions, and knowing the setting of 0.5 microseconds per division, that gives us a period of 1 microsecond. The frequency is the inverse of the period, so the frequency in our case is 1 over 1 microsecond, which equals to 1 megahertz, which is exactly what we set on the signal generator. And now the third subsystem that any oscilloscope has is the trigger system. If the trigger system is configured properly, you don't even notice it's there, so for the purpose of this demonstration I just disabled it. Now, even though we have a sine wave at the input of our oscilloscope, the image that we see on the screen is definitely not a sine wave. And that's due to the fact that now the time base of the oscilloscope is not synchronized with the input signal. So by having the time base free running like this, we can get all sorts of unexpected results. One possible solution to this is we can cheat and we can adjust the speed of the time base until we match the speed of the signal. Something like this. Maybe just a little bit more. And now, by carefully adjusting the speed of the time base, we can make the signal stable on the screen. But by doing this, we create another issue. And that is, now we are in an uncalibrated mode because we've used the fine adjustment of the time base, which means that we no longer know the horizontal setting of this oscilloscope. So we have no idea how long one horizontal division is. And the solution to this is to just trigger the scope properly. So basically the trigger system consists of a comparator that compares the input signal against a fixed signal that we can set using the trigger level knob. This way we can choose the level on the input voltage for which a new sweep will be produced. So what happens is that anytime the comparator changes state, it triggers a new sweep. By having the comparator trigger at exactly the same point on the waveform every single time, we trigger the time base at exactly the same point on the waveform every single time. So that produces a stable image on the screen, as we can see right now. So once again, by adjusting the trigger level, we can choose the level for which the time base triggers, and we can also make that level positive or negative. And now let's explore the other settings that the trigger system has. First of all, the trigger system has a source setting because the oscilloscope can be triggered from multiple sources. It can be triggered from the first channel, the second channel, from the line voltage, or we can even trigger the oscilloscope externally by applying a signal on this BNC connector. And also, the trigger system has 3 modes of operation: single sweep, normal mode, and auto mode. In auto mode, the time base is triggered periodically, but if the trigger condition is lost for some reason, then the time base is free running like this. In normal mode, the time base is also triggered periodically. However, if we lose the trigger condition, then the time base is stopped. And then we have the single sweep, which, as the name suggests, produces a single sweep once the trigger condition occurs. And by the way, understanding how the trigger system works highlights two of the main disadvantages of the analog oscilloscope with respect to the digital oscilloscope. First of all, the trigger point on an analog oscilloscope is always somewhere around here. In some cases you cannot even see it on the screen because it's too far on the left due to the reaction time of the internal circuitry of the oscilloscope. Depending on what you're looking at, this could be an issue. For example, if you're looking at an event that doesn't repeat too often, it is pretty much impossible to see what was happening before the event that you're triggering on. And also, everything that we see on the analog oscilloscope is in real time, which means that if you're looking at a very fast event that doesn't repeat too often, the event will quickly disappear from the screen and there is no way to capture it unless you have some sort of storage functionalities. So as you can see, with the signal off, the image just disappears. However, in rare cases, analog oscilloscopes have a storage CRT which allows you to store quick events and look at them for a few more seconds after they happened, something like this. Now with the signal off, we can still have an image of the signal on the screen. And now, since I've mentioned non-repetitive or non-periodic signals, let's take an example. One example would be the startup characteristic of a power supply. You probably know that whenever you turn a power supply on, the output takes a certain time before it reaches the final value that you set here. In our case, 12 volts. And that time it takes for the output to go from 10% up to 90% of its nominal value that is set right here is called the startup time or the rise time of the power supply. By the way, this parameter is really important in certain applications, so let's also measure the startup time of this power supply using this analog oscilloscope as a final demo before moving on to the digital oscilloscope. First of all, let's look at the settings here. We have a nominal voltage of 12 volts, and in order to accommodate that on the screen, we have a setting here of 2 volts per division. And now, by turning the power supply on or off, everything happens so fast that we cannot really see the startup characteristic. And also remember that this is an analog scope, so the image will quickly disappear from the screen. So let's see what we can do about it. Well, first of all, we have to slow down the time base a lot in order to be able to see the startup characteristic. Let's start by doing this. Maybe this is slow enough to have something. Let's just give it a try. Okay, this could be slow enough to see the startup of the power supply. So now let's adjust the settings just a bit. First of all, the trigger source should be channel 1. We have to trigger in either normal mode or single sweep. And now we need to enable storage as well, because otherwise the event will quickly disappear from the screen, as I said. Now we've cleared the screen and now we can turn on the power supply. It didn't trigger, that means that our trigger settings are wrong and we have to readjust them. So let's see, we could try DC coupling and move it on a positive value and see if that triggers the scope. It did. So now let's make the time base just a little bit faster so that we can better see the startup. Now of course it doesn't trigger anymore. Let's try AC coupling then. And this works. Okay, so I would say this is good enough. And now we have to do some more adjustments here. because in order to measure the rise time at 10% and at 90%, we have to take advantage of the 10% marking and 90% marking that we have here. That means that we have to align our signal with the 0% marking at 0 volts, and then we have to align the nominal value of 12 volts with the marking here of 100%. So now with the trigger in auto mode, I will adjust the vertical position with the signal at 0 volts. Actually the coupling is set to ground, and now we have to adjust the signal until we get to 0%, which is right here. Now we go to DC coupling, and now we turn on the power supply, and now we have to do variable mode like this and adjust the signal until we reach 100%, something like this. Now we have to double check. We are at 0, we are at 100%, so we are all set up for measuring the rise time. So let's turn the power supply off. Let's keep the vertical settings as they are, and now we are going to enable storage, clear the screen. Sorry, actually we need to go to normal mode first. Clear the screen, enable the power supply, and now we have to quickly press save to keep the waveform on the screen. That's it, I pressed save, and now we have to count how many divisions we have from 10% to 90%. So the signal reaches 10% somewhere in here. Let's say we are at the first vertical line, and at 90% we are somewhere around here, I would say. So we have 1, 2, 3, 4, about 4 horizontal divisions until we reach 90%. And now we have to look at our horizontal setting, which is 5 milliseconds per division. So 4 divisions multiplied by 5 milliseconds per division gives us a rise time of 20 milliseconds. And now let's talk about the digital oscilloscope. First of all, the digital oscilloscope still has the 3 main subsystems that the analog oscilloscope has. We still have a vertical setting, a horizontal setting, and a trigger setting. However, the digital oscilloscope is a lot more convenient, first of all because all the settings are already displayed on the screen. Then we never have to do amplitude or period measurements manually, because we can just hit the measure button and all these parameters will be displayed on the screen. Also, the digital oscilloscope has cursors that allows you to do measurements by manually placing the cursor somewhere on the waveform. For example, we can align the cursors with the peaks of this sine wave, and we can once again measure the period and the frequency, this time based on the cursors. So on the signal generator we've set the signal with a frequency of 10 kHz, and now by looking at 1 over dx on the screen we can see somewhere around 10 kHz as well. So already things are a lot easier with a digital oscilloscope. Also, the digital oscilloscope relies on memory, so the things that we see on the screen are not necessarily real time, which is a big advantage in terms of how the triggering system works and how we can store waveforms and see something that happened before we trigger the scope on a certain event. Another useful feature of digital oscilloscope is protocol decoding. Basically, if you're debugging anything that involves an Arduino or anything that involves digital communication from one node to another, you can simply press decode, set up the oscilloscope properly, and then you can see what sort of data is being sent from one node to another. So in the case of this oscilloscope, you can decode anything that involves I2C, SPI, UART, CAN or lean. And also, to highlight the convenience of the digital oscilloscope, let's repeat the rise time measurement that we did with the analog oscilloscope. So first of all, let's start with some vertical alignment. I will first set the oscilloscope to 2 volts per division, like this, and then I will align the signal with some of the lower horizontal lines that we have on the screen. Something like this. Now let's turn on the power supply and see if the signal fits on the screen. It does, so the vertical system is set up properly. So now in order to catch the startup characteristic, we have to set the scope to single sweep, set a positive trigger voltage, turn on the power supply and see if we can catch the startup. The time base is way too fast for what we are looking at, so we have to adjust the settings and try again. Now this looks much better. And now using the cursors we can actually measure the rise time. So the first horizontal cursor needs to be at 10% of our nominal value, which is 10% of 12 volts, which is 1.2 volts. So let's do this first. This one should be at 1.2, so right here. Let's continue with the second cursor, which should be at 90% of 12 volts, which is 10.8. Which is right here. And now using the vertical cursors we can look at the difference in time between the two events. So this one goes right where the horizontal cursor crosses the signal, and the same goes for the other one. And now looking at delta X, you can see the rise time of the power supply, which is once again about 20 milliseconds. Now back to some boring theory. That's because we cannot talk about digital oscilloscopes without talking about sampling and quantization. Sampling is the process of converting a continuous time signal to a discrete time signal. So what this means is that at the input of the oscilloscope we have an analog signal that looks something like this. Inside the digital oscilloscope, this analog signal is sampled at periodic intervals, meaning that it is measured at periodic intervals and the values of those measurements are stored in memory. So let's apply this to the waveform that we have here. So let's imagine we sample our signal at some periodic moments in time represented by these vertical lines. So now basically our signal only exists at the points where these vertical lines intersect our signal. So we know the value for our signal right here, 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 and here. Since our signal is now a discrete time signal, this means that we no longer know the value of our signal in between these lines. We'll get back to this later because we have a solution for this. The time difference between two of these lines is called the sampling rate and is one of the most important parameters of any digital oscilloscope. Now let's talk about quantization. Quantization is the process of mapping the vertical value of an analog signal to a discrete set of levels on the vertical axis. By having a discrete set of levels, let's say 16 of them, we can easily represent every sample in a fixed number of bits. In our example of 16 possible values, each value is represented by 4 bits as indicated by the base 2 logarithm of 16, which is 4. So let's say this is level 0. Since we decided to have 16 values, our values range from 0 all the way up to 15. Now let's find the closest approximations for our input signal. The first point is best approximated by 11. The next point is best approximated by 15. The next one should be 11. The next one should be 6. 6 once again, 10, 12, 14, 14, and 11. So as you can see, our signal only exists at discrete points in time, and it also has discrete values on the vertical axis. In some cases we need to convert this signal back into a continuous time signal, so for this we need a strategy for interpolating the values that we have here. So one way to do this is to use linear interpolation, which basically means connecting the dots by straight lines. So as you can see, the signal doesn't look like the original one. However, if we sample the signal at a fast enough sampling rate, and if we have enough resolution on the vertical axis, our approximation can be close enough for our purposes. So since I've mentioned this, the number of bits per sample is called the resolution. So as you can imagine, the values of the samples are stored in a buffer, which is obviously of finite size, and the size of the buffer is very important in a digital system and especially in a digital oscilloscope. So as you can see, the sampling process introduces some errors and noise, which makes signal sampling and reconstruction a lossy process. But this is the price we have to pay for all the convenient functionalities that a digital system has over an analog one. And by the way, all that you've seen here happens in a single chip or in an electronic module called an ADC, or analog to digital converter. And now you're probably wondering how to convert the numbers that we have here back into voltages. Well, let's start with the greatest number that we have here, which is the full scale value. Well, the full scale value is usually equal to the Vref, or the reference voltage of our ADC. And to make things simple, let's just say that this is 1 volt. The next thing that we need to know is the value of one of these steps. So this is equal to 1 LSB, or least significant bit, and 1 LSB is equal to the Vref divided by 2 to the power of n, where n is the number of bits. So in our case this is 1 over 16, which is equal to 0.0625 volts. So now, if you want to, you can convert all the values that you have in the buffer back into voltages by multiplying them by 1 LSB. So this value is 11 LSB, 15 LSB, 11 LSB, and so on. So at this point, you're probably wondering why I went through all the trouble of explaining sampling to you when we are just talking about digital oscilloscopes. Well, that's because in order to set up an oscilloscope properly, and also in order to choose a digital oscilloscope, you need to understand sampling. So the sampling rate is mentioned right here. We have a sampling rate of 1 gigasamples per second in dual mode, meaning a maximum of 2 channels active, and 500 megasamples per second when all 4 channels are active. If we think about the fact that it took me about 15 minutes to acquire 10 samples on paper, this scope can do about 1 billion samples per second, so we could say it's just a little bit faster than I am. And also keep in mind that the scope is not always sampling at full speed. The sampling rate actually changes with the time base, so in this case we have a sampling rate of 250 megasamples per second. Now the resolution cannot be found anywhere explicitly on the oscilloscope, but you can find it in the manual. In this case we have a resolution of 8 bits. This means that the oscilloscope can distinguish between 256 levels on the vertical axis. Comparing this to our 16 levels that we had on paper, we can say once again that the oscilloscope is slightly better. So what about the buffer size? Well, the buffer size is also in this corner of the screen, and it is currently 17.5 megapoints, or megasamples, or millions of samples. Remember that on paper we only did 10, so once again the scope wins. So what about interpolation? Well, interpolation is actually a setting that we have in the acquire menu of this oscilloscope. In this case we have X interpolation, which is exactly what we did on paper, but we also have a fancier sin of X over X interpolation. And now, since we are talking about sampling, let's talk about some traps for young players. First of them is aliasing. So whenever we have a sampling system, keep in mind that aliasing can occur. Basically, this means that the sampled signal can contain some spectral components that were not in the original system. And those components are a function of the sampling rate and the spectral components of the original signal before sampling. So here we have a 5 MHz square wave that goes into the oscilloscope, and so far it looks just like we would expect on the screen. But let's see what happens when we change the time base. So far so good. Let's keep going. And now we can see something weird on the screen. Let's do a single sweep. Let's change the time base once again. And let's use the measure menu. And now what we have on the screen is apparently a square wave at around 17 Hz. Obviously this signal doesn't exist in the original signal, so it's something that appeared inside the sampling circuitry of the oscilloscope. To prove that this is the case, let's repeat the experiment on the analog scope. So far so good, we have a square wave at the expected frequency. So let's change the time base to the initial setting of the digital oscilloscope, which was 500 milliseconds per division. And now let's use the storage mode once again to see if we have a signal at 17 Hz. Maybe this is just a bit too bright, let's try again. Let's try again. So as you can see, there is no such thing as a 17 Hz square wave in this signal. Now let's talk about another trap for young players, which is circuit loading. As you can see right here, this scope loads the circuit with 1 megaohm in parallel with a 20 picofarad capacitance. These two parameters vary from one oscilloscope to another and for one probe to another. In some cases, for example with fast signals or high impedance nodes, this loading matters and it can alter the behavior of the circuit you're trying to measure, or it can affect the measurements. Another trap for young players is that the probes need to be compensated. Without proper compensation, the probes can actually change the waveform when used in 10x mode. To do this, you connect the probe to the output calibrator of your oscilloscope, like this, and make sure to connect the ground as well, because it will make the signal a lot less noisier, as you can see. And now you need a really small screwdriver, preferably a plastic one which is specially designed for this, or a ceramic one, which would be even better. And now you have to adjust this trimmer capacitor that you have on the probe so that the probe is compensated. As you can see, the scope produces a square wave here, and you have to adjust this trimmer capacitor until the signal looks like a square wave. So something like this. And if you want to be even more precise with this, you can just change the vertical setting and really zoom in on the lower part of the waveform and repeat the process to get an even better compensation. I would say this is close enough. Another common mistake when using the oscilloscope is to short out some circuits by not understanding how the grounding system works. Let me show you an example. We have this power supply here, which is currently producing about 100 millivolts, and let's say we want to measure the output with the oscilloscope, but for some reason we want the positive terminal of the power supply to be connected to the negative terminal of the oscilloscope, something like this. As soon as we do this, we can notice that we've basically shorted out the power supply because the voltage is no longer 100 millivolts and it went to constant current mode and is now current limiting at about 5 milliamps. So that means that this sort of measurement is basically impossible with an oscilloscope unless we change something. Let's find out why. So let me explain what's going on. Here we have the grounding lead of the oscilloscope, and here we have the power cord for the oscilloscope, and this is the power cord for the power supply. And also here we have the terminals of the power supply. First of all, let's talk about the oscilloscope and see what's going on with this grounding clip. Well, this grounding clip actually connects to the case of the oscilloscope, and it also connects to the protective earth connection which we find in the socket. This means that whenever we plug this in, the grounding lead of the probe is connected to the protective earth in the power strip. Moving on to the power supply, something similar happens here. Let's test the negative terminal against the protective earth terminal that we have in the socket. So this is also connected to the protective earth, so whenever we plug this in, we basically have a connection between the ground of the oscilloscope and the ground of the power supply. And now let's replace the power supply with the multimeter and see how we get a dead short as soon as we connect the positive terminal to the grounding lead of the oscilloscope. Let's connect them and see what happens. As you can see, we get a dead short, which is caused basically by the power strip. And also notice how, for safety reasons, for the purpose of this demonstration, this power strip is disconnected from the mains. The solution to this is to always measure signals that are with respect to ground, unless you have a differential probe for your scope. In some special cases, you can probably also float the device under test, but keep in mind that this is a serious safety hazard if you're working with high voltages. So for this demonstration, the solution is much simpler than this, because I cheated a bit. This power supply is normally floating, but I connected it on purpose to the power ground. So by simply removing this wire, the problem is solved. So I hope this video managed to shine some light on the oscilloscope and how to use it, and if it did, please give it a thumbs up. And also make sure to check the description of this video, because there you will find some links to external resources that help you understand the topics of today's video even better. And finally, if you're interested into more content related to electronics and programming, please subscribe to this channel because there are more videos on the way. That's it for today, and thanks for watching. Bye!